All right, so last section in chapter 8 is on vectors. Okay, so again, this week it's all in the packet that I gave you. If you want to look stuff up in your book, it's section 8.5. But again, everything that I'm going to teach you is out of the packet. So first thing is what a vector is. Okay, a vector is used to measure any quantity, and there's two parts to it. Does anybody know the two things that a vector measures? Yeah, magnitude and direction. Can somebody think of something that has a magnitude and a direction to it? In other words, something that a vector would be really good at representing in real life. A what? What do you mean about a plane? A picture of a plane.
Velocity. And it's going somewhere.
Okay, so a plane could be represented by a vector because a vector has a magnitude, which is like the velocity. And what does it mean when it's going somewhere? It doesn't. Well, it does have a distance but it's more. It has a
speed.
That's the magnitude.
Yeah.
What else? Besides a magnitude, it has a direction. Okay. So, those are two things you could model with a vector. You could model anything that has a velocity. So it could be throwing an object, it could be a plane or a car traveling. Anything that has velocity, right, that's the magnitude, and taking into account the direction. Force is another example. So force, when you push on an object, there's a certain how hard you push, okay, certain amount of force you push, and there's a certain direction you're pushing in. Okay, pushing to the left with a certain amount of force is different than pushing to the right. Okay, different direction. So I have a picture. We can just take a look. Those just represent different airplanes flying, and you could think of each plane as a vector. Okay, each plane has a certain direction to it, the way it's traveling, and a certain speed. The thing that's a little complicated is this is really 3D, because planes can also have an altitude to them. So two planes that look like they're close, one might be on the ground and one might be up in the air. Right? So keeping track of all these different planes, they have the airports with the air traffic controllers, and computers can basically think of planes as vectors. That's how you could represent them in a computer. Right? And if you zoom out, there's
What did you say?
tons of these planes. There's probably thousands, tens of thousands of planes all in the air at the same time. I don't know if I can zoom out a little bit. So as you zoom out, you can definitely start to see where airports are. So if New York over here, and then DC, and then
Los Angeles. Yeah, I bet Orlando's
airports.
back too.
Yeah. So there's a lot of these planes in the air, so you got to really keep track of them. And vectors is a pretty good way to do it.
Do those represent like the small, like little two-person planes too?
I don't know if every single plane or if it's just commercial or stuff like that. Yeah.
You seen the double-decker landing in Boston?
Nope, I did not.
Okay, so one way we can draw represent a vector is by drawing an arrow. Okay? And an arrow is perfect because the length of your arrow is the magnitude, and the direction it points, well, that's the direction. Okay, drawing out the vectors, that's really helpful when we do some word problems. Okay, we're going to look at some different things we can do by drawing. Like we can add vectors by drawing them, we can subtract by drawing, things like that. But really, the most helpful time you want to draw vectors is when you have a word problem. Okay, one disadvantage to drawing is that you usually, if you want to do things to scale, you need some kind of graph paper. If you want to draw things nice and straight, you also need a ruler or some kind of straight edge. Okay, so when we draw a vector, okay, as an arrow, it's basically like a ray. You have the starting point, which we call the initial point, and the terminal point. Okay, in my picture, P is the start point, Q is the terminal point. What would happen if you switched P and Q in terms of the vector? What would change about the vector and what wouldn't change?
Its direction would change, but its magnitude wouldn't.
Right, if you switch the initial and terminal point, the direction changes. In fact, it's like rotating it 180 degrees, but the magnitude doesn't. Okay. If you want to label a vector, if you want to give a name to this, like in geometry, you'd normally say ray PQ. Well, when we're talking about a vector, there's two ways to do it. You can either put a letter with an arrow over it, and the arrow on top of the letter doesn't indicate direction. The arrow on top, it always points to the right. It just represents what's below it. The M is a vector. Okay? Or you can write it as a bold letter. If you look at your packet, all the formulas on page 335 in the packet, you can see they use bold letters. Right, so you can do it either way. If you don't bold it or you don't put an arrow above it, then it's just a variable. Okay, like in algebra. Okay, so sometimes on the board, if I have it already drawn, I can easily make things bold just by clicking on it and changing the thickness. But if I'm actually handwriting it, I usually use the arrow because that's quicker, at least on the smartboard. All right, so one thing this week we want to try to make sure we understand is what happens when we take vectors and combine them different ways. Okay, what do you get when you do that? So the first one we're going to look at is adding. Okay, if you add two vectors together, okay, you get a new vector. Okay, one way to think of it is like, let's say if you were pushing on something, like if there was an object here, okay, and you were pushing up on it, and then somebody else was pushing right on the object, what direction would the object move? Huh?
We go up, yeah, and then over.
It'd go up and to the right, yeah. So what would happen is the result would be a new vector with a direction up and to the right, and there would be a new force. If you have an airplane, okay, flying, and it's flying with the wind, okay, the airplane has its own velocity, magnitude and direction, and then maybe the wind is blowing, if it was exactly behind it, it would be blowing it forward, so the plane would go faster. Okay, the plane would be traveling in the same direction if the wind was exactly behind it, but it would blow it faster. Okay, so it's, whenever you combine two vectors, you get a new vector. Okay, and we're going to look at an example with airplanes tomorrow. We'll look at like a plane flying in a direction, and then there'll be a wind blowing, and we'll figure out how much is the plane going to get blown off course. Okay, what direction is the plane end up traveling if the pilot doesn't take into account the wind, and how fast does it go? Okay, the wind can either speed the plane up or it could slow it down, depending on which way the wind is blowing. So when we do that, since that's a word problem about planes, we're going to do it graphically. Okay, we'll look at how do we add the two vectors visually. Okay, so that's what I'm going to show you right now. Okay, to write the whole thing out, it's kind of a lot to explain, but here's the kind of simple idea. If I want to combine that vector in black with the one in red, all I have to do is line them up, just like that. Okay, line up the end of the one in black to the beginning of the one in red, and then connect where you started to where you stopped. Okay, so what's in green right there, that represents combining the black and the red vector together. Okay, so the black is pushing up and to the right. The red one is pushing down and to the right. So the final answer is still to the right, but the red one is pushing down a little bit more than the black one is pushing up. That's why the final answer is going down just a little bit to the right. Okay, so now I'll just explain kind of what we just did. So position the two vectors, V and W, so that the end point of V and the initial point of W are right on the same spot. Right there. Okay, after you line them up that way, then draw from the initial point of V to the terminal point of W. From here to there. And once you draw that, that's the answer. Okay, so doing that on graph paper, you can get a really good idea of things, really doing it to scale. If you don't have graph paper, then you can get kind of a general idea, but it's not something you could actually, measure with grid lines, because we don't have any on this paper, on this whiteboard. Okay, also, make sure you connect it in the right order. Okay, if you did something like this, let's flip this up and down, and left and right. Okay, what I just did is basically equivalent to rotating 180. If you do a flip, a reflection horizontally and a reflection vertically, it's a 180 rotation. Now, this is wrong. Okay, this is exactly the opposite direction that you should get. Okay, so any questions on the steps to add vectors visually? It doesn't just have to be two vectors. You can stack as many together as you want. Okay, if you had a third one going that way, you still just connect where you started to where you stop. Okay, but the thing is, all the arrows should be pointing in the same direction. Okay, so if you follow it, it should kind of make a path. If you did something like this, now that's not right. Okay, try to think of it as like pipes in a building or something, right? Everything, it should just flow, one way. It shouldn't go back the other way, like this one is.
So what if you have one drawn like that?
Well, if you were adding them together, these would be positioned wrong. You should have positioned it. Where's my other pen? You should have positioned it so maybe this point was over here. Yeah, you always position the beginning of one to the end of the other. All right, so we'll add these up. And specifically, I want to do V plus W. So that means W gets added on to the end of V. All right, so there's V. Take W, put that on it. And then just draw in your final answer. So it's kind of hard to show it in your notes, but what you could do is just draw the two vectors and then draw the final answer in a different color. What I usually do is I move it away so you can see it after. Okay, so that's V, W, and that's V plus W. And it should make sense when you're done. If V is pointing down and to the right and W is pointing to the right, combining the directions I just said is something that goes even more down and to the right. And that's V plus W. Okay, any questions on that? So one kind of question I could give you on a test is I could say, here's the two vectors, the V and W, and give you four choices what you get when you add them up. Okay? I could have this one, I could have one pointing exactly the opposite direction, and I give you two other choices. Okay? But that is the correct answer. All right, what's going to happen here? Yeah? Yeah, what's going to end up happening is if you want to take V and put W on the end of it, take the ending point of V and line it up with the starting point of W. It's kind of hard to see once they overlap, but what I need to do is line those two red dots up. And then once I line those up, I need to connect the start point of V to the end point of W. So my final answer is what I get when I connect those green dots. after lining up the red dots. Okay, so that's what I'm going to do. Line up the end point of V and the beginning point of W. Now they're lined up. And now connect where V started to where W ends. Well, they're exactly the same point. So they do, it's kind of like they cancel out. So there's no magnitude here, there's no direction. How would I write that answer?
N equal.
Okay, so it's like everything is balanced. We're going to talk more about equilibrium tomorrow too. Does anybody know what you can write down though? Kind of the, because what did we say? When you add two vectors, the answer is always what? A new vector, and that's still true here. The answer is a vector. But does anybody, it's a special vector. Anybody know what we call it? Not sure? It's called the zero vector. Okay, not zero the number, but zero the vector. Okay, it's the only vector that doesn't have a magnitude, and it doesn't have a direction. So
draw the arrow on that way from off of it.
the arrow, yeah, it's just like in geometry. If you want to write like ray AB, in geometry, when you write a ray, you always put the arrow going to the right. You don't ever really do something like this in geometry. This is always the symbol you use. Yep. Okay, so any question on that? Okay, so make sure when we're doing that you always put the arrow on top of it if you're talking about a vector. If you're doing something numeric, okay, like negative, like you're adding numbers like -2 plus 2, that's the number 0, okay, not the vector 0. All right, what does commutative mean? If I'm telling you vector addition is commutative. Yeah?
You can switch stuff around, like 2 plus 1 equals 1 plus 2.
Yeah. Basically means with commutative, you can switch the order. And you will get the same answer. And you might be like, well, yeah, isn't that always true? No. We have to make sure it still works with vectors. Because the commutative property, when we get into multiplication with vectors, doesn't always work. Depends. I have to be a little more specific, and we'll get to that on Wednesday. But just because something we know it always has worked with numbers doesn't mean it works with vectors. The commutative property for addition, though, does. It does work. Right, so this part, really, you could just kind of watch how this works. I'm going to do V plus W first. Okay, the way I just lined those up, that's V plus W. And I don't have a grid, so I'm just kind of estimating it the best I can. Okay, so off to the right is V plus W. Now I'm going to switch it. I'm going to do W plus V. So I'll take W and then add V onto the end of it. Any question on how I line them up to do W plus V? Just kind of switch which one comes first. Okay, and I'm going to draw in the answer. And now I'll compare the two, and they should be pretty close. They come out the same. They're close. So what I'm just trying to show you is that the vector addition is commutative. Okay, you can switch the order. How about associative? What does that property mean? It means the same thing here as it does with numbers. Yeah?
It doesn't matter which two you add first.
Yeah. It just has to do with kind of the precedence, which one you do first. So if you do A plus B first and then add C, or do B plus C first and add that onto the end of A, you're going to get the same thing. So I can, I'll show you that. First, let me do it the way on the left. Take A plus B. I'm just going to kind of draw that one by hand. So I get A plus B. plus u. And then I'm going to add c onto the end of it. Okay, so the answer that I get is basically it would look like that, connecting where I started to where I stopped. Any questions on that? Okay, now I'm going to do it the other way. Keep in mind, I drew all these by hand, so might not be perfect. All right, so now I'm going to take B and add C to it. So there's B plus C. Okay, so we'll start with that. And now I'm going to add A. Well, I'm going to do A plus what I just did in red. So there's A, and there's what I just did in red, B plus C. So I'm going to do that. And if I compare the two answers, that's not bad. They're pretty close. All right, so the point is the associative property works. Okay, what's the difference between vector v and the vector negative v? Kind of talked about this earlier, but we didn't write it exactly like this. Yep. Can you be even more specific about the way it points? It could be right and left. But it is direction. But I just want to be a little more specific than the other way, but not so specific as left and right. So kind of I'm looking for something in between a little bit. Yeah?
Negative v goes in the opposite direction.
Yeah, it goes in the opposite direction. It could be left and right. It could be up and down. It could be up and, it could be a lot of different things. But the point is the direction they point. They have exactly the same magnitude, but they point in opposite directions. And what would you get if you add those two vectors up? The zero vector. So what I have on the board right there, technically that's wrong. You don't add two vectors and get a number. You add two vectors and get a vector. And basically the zero vector, we'll talk more about that, but it represents what we call static equilibrium. Okay, if you think of like a tug of war and the rope isn't moving at all, it's not because there's no tension in the rope. There's a lot of tension in the rope. It's just because the force pulling right and left is balanced. So the effect is basically zero movement. Right, so how do you think I could do something kind of along this idea to add, subtract two vectors? I want to do it visually like I did before. But how do you think I could do v minus w visually using those two arrows? Yeah, if you think of this as v plus the opposite of w, which is exactly what I have written right here, that's how you can subtract two vectors. We really do it as an addition problem, and we just add the opposite of the second vector. And by finding the opposite of a vector, we're not changing the magnitude, we're just changing the direction. Okay, so if I want to add those up, the first thing that I need, just do all these the same, is that. Okay, I need negative w. Okay, if you're sketching it by hand, all you'd have to do is really draw the same length arrow, just point the other way. If you have a computer or something like that you're sketching it on, you just need to rotate it 180. Or I don't have that option, so I can just flip horizontally and then flip it vertically, and it will reverse the direction. Okay, and it keeps the magnitude exactly the same. Okay, now I'm going to take V and add negative W onto the end of it, and that's like subtracting. Okay, so here's V and negative W, and that's V minus W. Any questions on that? So as far as arithmetic or basic operations that we're doing with vectors, addition and subtraction are the only two we're going to do visually. Multiplying a vector times a vector, we're going to look at that on Wednesday and Thursday. We won't be doing it by sketching though. And eventually we're going to get away from sketching to do addition and subtraction. If you just want to add and subtract vectors, it's a lot easier if we just had numbers that we could work with rather than having to get graph paper and a ruler and all that stuff. So, but still very, very good for word problems. Okay, but that's the only time I really draw it out like this. All right, so next thing we're going to look at is multiplication, but we're not going to look at multiplying a vector times a vector. Okay, I just said that would be Wednesday and Thursday. We're going to look at what's called scalar multiplication. Okay, scalar multiplication is when you take a vector and you multiply it by a number. So it's a number times a vector. And that number is called a scalar. Now, if you scale something, what does that mean if you scale something? If you make a scale model or a scale drawing, why do they call it a scale model? What is that? It's what? It's not the actual size. So what size could it be? Could be smaller. Could be bigger. Yeah, you might make a scale model of a cell or something, and it's a bigger version of a cell. Or smaller, like if it's a house, you might draw it on blueprints and say, 1 inch equals a foot or something. It's a smaller version. But there's one more thing that can happen with vectors if we multiply them by a number. They can get longer, they can get shorter, and one more thing. They could stay the same if you multiply by 1, but I'm thinking something else. Yeah?
They can change direction.
How would they change direction?
If you multiply it by a negative,
Yeah.
it would change the opposite direction.
Yep. So a scalar can do three things. Make it longer, shorter, or it can change the direction. Okay, so again, that's called scalar multiplication, because you're taking a vector and you're scaling it. And possibly changing the direction if you multiply by a negative. So sometimes we might have a vector and we want to scale it so that it's 1 unit long. Okay, that's kind of a special case. We call that a unit vector. And we'll talk more about those either later today or tomorrow. All right, so let's look at this one. How would 2v compare to v? What would be the difference between them, or what would be the same? The direction would be the same. Yeah, direction's not changing, but the magnitude is. How is the magnitude of 2v compared to v? Yeah, it's twice as long. So if you really want to do it to scale, all you have to do is take v, make a copy of it, and add it onto the end of v. And v plus v, there's 2v. not a very convenient way if you had to do like 30V, because then it's going to take a while. In that case, we'd probably just want to work with numbers and write down the answer rather than draw it. Okay, and for the 1/2 V, I don't really have a good way to sketch that exact. I just kind of have to estimate it. So 1/2 V, probably be about like that. Oh, that one. And notice when I put the vector symbol on it, it doesn't go over the 1/2. Okay, the 1/2 is a number times the vector. Okay, we also don't put any symbol between the 1/2 and the V usually. Like sometimes in math you use a dot. We want to be very careful using the dot in this section. This means something very special if you put it. Okay, and we'll talk about it on Wednesday. And at this point in math, you normally don't use the X anymore for multiplication. Kind of in grade school you do that. But we also want to be very careful if we put an X between two things, because that means something very different as well. Okay, so some symbols that you're used to seeing in the past kind of have the same meaning, but it's also a little bit different. Okay, and with vectors, it actually makes a difference which one of these we use if you decided to write one. All right, so negative 1V. Okay, it's just like what we did earlier. It's like negative V. So I'm just going to estimate it. So that's negative V, same direction, just points opposite direction, same magnitude. That's all. And then negative 1/3 V, it's going to point the same way as the one I just did, but be about 1/3 as long. Okay, so that's negative 1/3 V. Any questions on that one? All right, so now we can kind of take that idea. Let's just do one of those. Do you guys want to try the first one or the second one? First one? All right, so 2V plus 3W. What would I do first there to figure this out? Kind of want to break it down into like steps. Yeah, let's make 2V first. I'm going to kind of look at V and W to figure out where should I start on the grid, because I can start anywhere I want, but preferably I'd like to stay on the grid. V is going up and right, W is going right. So I want to start on the left side of that grid, maybe kind of in the middle area, and then I should be able to stay on it. Okay, so there's V, and we'll put another V. Okay, and then on to the end of that, I'm going to add 3W. Do I need to switch the direction? What do you think, Ayla? No, because we're not subtracting. If we were doing the second one, we would have to find the opposite of W. Okay, but this is just taking 3 of those and putting them on the end. Okay, this time, I think I made them so they the terminal points land always on a whole number coordinate, integer coordinates. That doesn't always have to happen. But if I'm going to ask you to sketch something, I'm probably going to have it start and end on nice numbers. Okay. And then answer is like that. Okay. What I usually do, I like to move it off the arrows a little bit, because it's a little confusing, I think, when you draw it like that, because you can't even see the arrow. But you can do two things, either make it a different color or move it off a little bit. Now you can see it a little better. Okay, another thing you could do on paper is if you have it drawn and it looks kind of like this, just make the arrowhead bigger. So I can see which way it's pointing a little better. Okay, however you can make it clear. Any questions on that? All right. Okay, so that's symbol. When you put double bars, okay, they don't really call it double absolute value bars. They just these double bars. That symbol represents the magnitude of the vector. And because magnitude is a length on the arrow, think about what kind of numbers length always is. It's always positive. Okay, even if you're driving, like in a car, magnitude is always positive. If you want to go in reverse the other way, that's a different direction. It's not a different speed. It's not negative speed. So what would be the difference between the magnitude of the vector v and the magnitude of the vector negative v? Nothing. Those are exactly the same thing. So that, for example, that's like if you were measuring the distance from here to your house or from your house to here. It's different directions, but it's still the same distance, same magnitude. Okay, I mentioned this a little bit earlier. If you have a vector that's exactly 1 unit long, okay, it's called a unit vector. We're going to talk a lot more about unit vectors. And we've seen the word unit before. Does anybody remember what other topic? Yeah, I was going to say what other unit we did, but that's kind of confusing. Yeah, when we did the topic on unit circle trig. It was about circle with a radius of 1. Okay, so that word comes up a couple different times. Okay, any questions, or anybody still needs a copy? All right. So if we really want to start to get into doing things with vectors, we need a better way than drawing them. Okay, as I said, drawing's great for word problems, but in general, it's kind of nice. Like if you just want to add 2 vectors, can we just do it with numbers so we don't have to sketch it? And we can. There's a couple different ways we can do it. One way we can write a vector, according to our book, they call it an algebraic vector. And how about in physics? Does anybody, actually there's only one person in here that's in physics, right? Yeah, Dave just left. In physics, how do you write vectors as like numbers? Like if you don't want to draw it, what do you write down? Do you have a way you do it? Okay, we write down components, and that's pretty much what we do here. We write the components. We use these brackets. I don't know if other classes use that symbol, but we use that to make it clear that whatever's in here represents the components of a vector. If you don't put brackets, it's just a list, something, comma, something. And then if you put parentheses, that's an ordered pair. Okay, so an example, I'll come right back to this, but an example of a vector would be just like that. It's the vector 2, 3. And what the 2 and the 3 represent are the horizontal and vertical components of the vector. Okay, and what we mean by that is any vector that's on an angle, okay, you can break it down into a triangle, just like this. And by drawing a right triangle out of it, you can figure out the horizontal component, which is in this case, to the right, and the vertical component, which in this case is up. So those 2 arrows I drew in blue would represent the A and the B. And when you add A and B together, you get what's in red. It's exactly what we just did visually. So all that this form tells you is basically A tells you how far to go left or right from a starting point, and then B tells you how far to go up and down. But this notation doesn't tell you something. So in a second, I want to sketch the vector 2, 3. So the 2 tells me something about horizontal movement. The B tells me something about vertical movement. But what doesn't it tell me? Yeah? Well, I'm going to get the direction because I know where to start and I know where to stop. Well, I know to go from some point to some point. So the A and the B are the direction. But it doesn't tell me something. Yeah? It doesn't directly tell me the magnitude, but I think we could figure out the length of this line in red, right? If we know A and B. How could we figure that out? Yeah, we could do the Pythagorean theorem, and we'll talk more about that some point later on. So look at that vector. Now, if I asked you to sketch 2, 3, what's the first thing you'd have to figure out?
Like where it starts.
Where to start. Okay? So this notation does not tell me where to start. I could start here, but once I decide I'm starting there, then I know the direction to go. Right 2, up 3. So that's the vector 2, 3. I could start over here, right 2, up 3. That's also the vector 2, 3. Where do you think a common place to start is, though? Yeah, a lot of times we start from the origin and go from there. Okay, so if your initial point is at the origin, okay, we call that a position vector. Okay, so my question here is, this notation doesn't tell you the position to put the vector in the plane. But if you're given a choice, start from the origin. So now what I want to look at is if they give us an initial and a terminal point, not at the origin, not starting at the origin, how can we convert two coordinates into a vector like I just circled in blue? Okay, so I'm going to take one of the arrows that I just drew on the other page. To make it simple, I'm going to drag it to quadrant 1. And I want to convert it to a vector. Okay, so let's take this one, and let's put it right there. Okay, let me make it a little bigger so you can see it better. What's the coordinates of the initial point? We'll call P the initial point. Yep, 4, 4. So that's point P. And how about, we're going to call point Q the terminal point. What are the coordinates of that? 6, 7. So if all you were given were those 2 points, and they didn't give you the picture, how would you convert these coordinates into the vector? We already know the answer. It should be 2, 3. Can you be more specific? Subtract P from Q. Yeah. Take the terminal coordinate minus the initial coordinate. And that'll convert it into a vector. Okay, just by subtracting. Okay, so you could call them P and Q or P1 and P2, whichever one is the initial and terminal. Take the terminal coordinates, x2, minus the initial coordinate, x1. And then do the same thing for the y's. Take the terminal part of the coordinate, y2, minus the initial part, y1. All right, so we'll try finding a position vector given two coordinates. Okay, so there's our problem. Okay, if they don't tell me which one is which, always assume P1 would be initial, P2 comes after it, that would be terminal. Okay, so what would be the x value? What would be the x value of my coordinate? Of my vector, sorry. What would be the x component? Amanda? Yeah, it would be 5. How'd you get that?
4 minus, and then
Yeah, 4 minus -1. So you know what, actually I'll do it in 2 steps. So. And what about my y value? Yep, it's going to be 6 minus 2, which is 4. So that's it. And extending this to 3D, okay, just for those that aren't going to be here, isn't really that much harder. In 3D, you've got a coordinate not with just an x and a y, but you've got an x, y, z. And you do the same thing, except you have to do it one more step. Okay, and that's all that we really do in 3D. Everything is one more step. So you subtract the x's, you subtract the y's, and you subtract the z's.
what did you do, 1, 3, 4?
Yeah, thank you. Why did I write that? 2 minus 1 is 1. 5 minus 2 is 3. 1 minus 5, -4. Okay, so that's it. Just that little extra step on the end. Hey, we'll talk more about that on Thursday. Hey, any questions on that? All right, people feel okay with that stuff so far? All right, let's take a look a little bit at the second part. The second part gets into word problems, which we're not going to get to that today. But just talks more about doing things without drawing vectors. Okay, so in this section, or same section, in this part, they pick up right with where we left off, writing vectors in that algebraic notation. And what do you think it would mean for two vectors to be equal to each other? I said this vector is the same as that vector. What does that mean?
They have the same magnitude and direction.
Yeah, they have the same magnitude and direction. What it doesn't mean is that they're drawn in the same spot. That vector is exactly the same as that vector. Even though if you wrote their initial and terminal coordinates, if we had a grid here, they wouldn't be the same. But these two vectors have the same magnitude, they have the same direction. Okay, so that's what it means for two vectors to be equal. Not an overly important idea, but something that, just to make clear. questions on that? All right, so we've learned so far two ways to represent vectors. The first way is draw it as an arrow. Second way is the algebraic notation with the brackets. And the third way, and this is the way that we use most often, and it's very similar to the last way we just did. It's not drawing, it's more like writing numbers. It's called unit vector notation. What's a unit vector again? What does that mean about the vector? Magnitude is 1. So I'm going to show you two special unit vectors. Does anybody know the names of from physics? There's two special unit vectors in 2D. If you're doing 3D, there's 3, but we're doing 2D. Okay, the first one is vector I. Nothing to do with complex number I. That's totally different. But the vector I, when you're doing vectors, I means it's a unit vector, and it points 1 unit to the right. Okay, if you want to see a picture, I'll come right back. That's a picture of the unit vector I. It's 1 unit long, and it points right. Okay, J is another unit vector. So it's 1 unit long, but this one points up. And if you want to see a picture of that one, there's the unit vector J right there. It's 1 unit long, and it points up. So the last notation for writing vectors basically uses, think of I and J as like building blocks. You stack I's and J's together to build whatever vector it is you want to build. Okay, so that's what I'm going to show you right now. Okay, how we can use I and J to build vectors. All right, so I'm going to build the vector 3, 4. Okay, so I'm going to sketch it, so we already kind of know what we're looking for. I'm going to draw it as a position vector. Start at the origin. I'm going to go 3 right, 4 up. Okay, and just to make it different colors, the red is my initial point, the black one is my terminal point. Okay, let's start with the eyes. Okay, that's the horizontal. How many eyes would I have to stack together to get me from the initial point towards the terminal point? Yeah, we need 3 of them. So we need 3 copies of it. And then just, you know what I should do though? I should, let's make them a different color. Since they're going to be right on the axis, you won't see them very well. All right, so I've got 3 eyes. And how would we represent that numerically? I. So that's 3i. And then I would have to put what onto the end of it to get me to my terminal point? I would need 4 j's. And let me see if I can make some copies. These won't be on the axis, so you should be able to see them. I just messed that one up. It's a lot easier if you have your mouse. All right, so let's just take 1, 2, I think I messed that one up. 3, and 4. So there's our 4i. And what is the operation between the i's and j's? What did I just do with them? I added them. And that's it. That's the notation for writing a vector using what's called unit vector notation. It's just 3i plus 4j. And you could draw it if you want to draw the final answer, but I just wanted to show you that. Now, what would happen if I wanted to land here? What would I have to do a little bit different on this one? Yeah, I'd have to use a fraction of I. I might have to use like 6.5 or 7.5 I. So using halves or thirds or whatever decimal you need can get us anywhere in quadrant 1. But how could I get over in one of these other quadrants? Negatives. I could have negative 3i or negative j, and that could get me in any one of these quadrants. So the term here is we can say that these two vectors, I and j, they span the coordinate plane, meaning you can get from anywhere to anywhere stacking them together. They don't span 3D space. Okay, for 3D space, you need one more. Basically, you need as many unit vectors as you have dimensions to cover or span the entire space. If you only had one vector in a 2D space, you would be stuck moving in a horizontal or just a vertical direction. Okay, so that's the idea of unit vector notation. All right, so the last thing I'll show you is formulas for adding, subtracting, scaling, all the things we just did visually, but now just doing it with numbers. Okay, so in the formulas I'm going to show you, the v and the w, those are going to be vectors, and alpha is going to be a scalar. Okay, if you want to add vectors v and w, okay, rather than drawing it out and connecting the ending point and the starting point and then drawing in the diagonal, all you have to do to add two vectors visually, or not doing it visually, is take the x components, add them up, bless you. Take the y components, and add those up. So now we've got a way to add two vectors without drawing anything at all. Okay, how about if I wanted to subtract two vectors? What do you think would change in the formula up above? Yeah, all you do is x1 minus x2 and y1 minus y2. You've got to be careful with subtraction because the order matters. With addition, it doesn't. And we already know that because we said the vector's addition was commutative. Okay, the next one here, alpha times v. Alpha is a scalar. This is scalar multiplication. Okay, what were the three things that a scalar could do? Well, shortening and lengthening, those are both changing magnitude. It could exactly reverse the direction. Well, instead of doing it visually, all you have to do if you want to scale a vector is multiply the horizontal component by the scalar and the vertical component by the scalar. So it's almost like a distributive property. Okay, and the last thing we kind of already talked about, I already asked you guys, and most people seem to know the answer, how you can find the length of a vector. So, does everybody have up to the scalar formula? Right, so if you want to find the length of a vector, that's v. What shape did I break that down into earlier? Yeah. All you need is a horizontal and a vertical. Okay. Put in those two lines where they should go. There we go. And I just made a triangle out of it. That's my horizontal. That's my vertical. The horizontal component of v was x1. and that's y1. So how would you find the magnitude of v? Yep.
Using Pythagorean theorem, so, the square root of x squared equals 1.
Square root of, yep, x1 squared plus y1 squared. That's it. That's the formula for the magnitude of v. It's just the Pythagorean theorem. Okay, so tomorrow we'll pick up with that and we'll do one of each type. All right, so for homework tonight, okay, that's the homework on 5.4, the first part. Okay, I erased that because if I hadn't explained the I and J part, you wouldn't have been able to do it, but you should be able to do that. Okay, so 1 through 10 all, 14 to 22 even, 26 to 32 even. Okay, does everybody have that part? Okay. And then we didn't really get into much of part 2. Let's see. Let's see, yeah, we can't do anything past 47. So try, and 25 to 31 you already did. So try, let's do 33 through 5, 7. Let's do 33 to 43, just the odds. Okay, that's using the formulas I just went over. If you have trouble with them, that's okay. We'll go over them tomorrow, but I think they're pretty straightforward.